speaker is Niklas Beisert from Institute for Theoretic Physics, Switzerland, and he's going to talk about classical Bialgebras for AdS CFT integrability by contraction and reduction. Nick, can you share your file?
I could try. Let's see. Where is it?
It's nice to be here in my office and to record my talk, Classical Bialgebras for AdS CFT Integrability by Contraction and Reduction. I would like to thank the organizers of the second International Conference on Holography and its applications for their invitation and for presenting this recording to you. Hopefully afterwards, after presenting the talk, there will be some opportunity for a live discussion. In this talk, I would like to present some research we started a while ago with this paper of a particular case that we studied there. We continued more recently together with my doctoral student, Igor Im, in this paper and in some ongoing work. I would rather like to present the context in this talk, the context of the research, and motivate why it's interesting to us. And then also sketch out some of the details, some of the results that we obtained. So this talk, the context of this talk is the AdS CFT correspondence and a particular worldsheet S matrix that comes to use in that context. For the purposes of this talk, AdS CFT will always refer to AdS 5 strings and n=4 super mills. And that's a particularly interesting system because in the planar limit, it apparently becomes integrable. There are a few other systems, some other AdS CFT pairs of models that also share this feature, but I will, for simplicity, only focus on this one, but the other results are also quite similar. Apparently integrable here refers to the fact that we don't quite know whether the system is integrable, mainly because we don't even know precisely what is integrable in the first place, but it has led to very interesting results. In particular, it has led to an exciting and fruitful scattering problem on the two-dimensional worldsheet. So there we consider the field theory that lives on the two-dimensional worldsheet of the string. In this scattering problem, you start with a vacuum, which essentially is a string contracted to a point, which is moving at the speed of light on the AdS 5 space, or in the corresponding gauge theory, it would be a half PPS local operator. This vacuum you can excite in certain ways, and these excitations are called particles or quasi-particles. And as usual in string theory, there are 8+8 bosonic and fermionic excitations of the worldsheet corresponding to the 8 transverse directions of the string. And they also have a corresponding nature in the gauge theory as magnons. In this particular system, these 16 excitations can be grouped together in a 4x4 matrix or supermatrix, and that is useful because it's very much adjusted to the symmetries of the problem. The residual symmetries of the problem are 2 copies of PSU2/2, which is a particularly superalgebra, and these are the stabilizer of the vacuum. That's what leaves the vacuum state invariant, and that's why the particles typically transform in representations of these 2 symmetry algebras. Here it would be the rows and the columns transform independently in a fundamental representation of these 2 copies of PSU2/2. And that's very helpful because typically the S matrix, the scattering matrix structure factorizes along the same lines, namely that the S matrix acts independently on the rows and on the columns by a smaller matrix, which I'll call R. And well, in addition, there might also be an interesting scattering phase, scalar phase, which has some intricate dependency on the particle momenta. but I will not really touch too much on this phase in this talk. I will focus largely on this factor R here. Also, the higher particle S matrix factorizes because this is an integrable system, and as usual, scattering factorizes into a sequence of two-particle scattering matrices. And this two-particle scattering matrix is special because it obeys the Young-Baxter, or satisfies the Young-Baxter relation. This scattering picture has many useful applications. First and foremost, maybe the determination of the spectrum for this string theory. This is even non-perturbatively described through certain types of integral equations. And that exploring these equations has been a very fruitful exercise a couple of years ago. But in more recent years, the focus has shifted towards correlation functions, which can also be expressed through integrable technology, as well as a connection to gluon scattering processes in this n=4 Mills theory, especially in the planar limit. You can draw some mileage from study of this system. Before I go further, I want to explain you a bit what the role of this R matrix is in integrable systems. So this R matrix is a scattering matrix, and it acts like an operator on a tensor product of two spaces, and it satisfies the well-known Young-Baxter equation, which is this one. Such an R matrix is a hallmark feature for quantum integrable systems, and there it really serves as an essential tool for all sorts of purposes. So I want to give you an example of R matrices in some sample integral system. That would be the Heisenberg spin chain, which is also sometimes known as the 6 or 8 vertex model. Here we have two states, a spin up state and a spin down state, and of course all linear combinations of these. So we deal with the space C2. And this R matrix acts on a tensor product of two of these spaces. For each space, there's also an associated complex parameter U, which plays some role, which is known as the spectral parameter, or also in this scattering context as the particle rapidity. And obviously, the R matrix, which is the scattering matrix, is a function of these two rapidities. Now, as I said, the R matrix acts on a tensor product of two of these spaces. So we have four basis states for two particle states, two spins up, two mixed states, and two spins down. And as such, the R matrix acts really as a 4x4 matrix, and one can look at the structure of this matrix. Now, for the Heisenberg spin chain, there are two general structures and three main cases that you distinguish. These are called XXX, XXZ, and XYZ, depending on some residual symmetries and relations. For these two, you get this block diagonal form for the R matrix, and it has 6 non-zero elements, and that's why it's called the 6-vertex model. And then there's the XYZ case, where you have two additional non-zero elements. That's called the 8-vertex model. If you look at the dependence of these elements on the rapidities, you find that typically these are either, well, first of all, you can always write it in a difference form. So R is a function of the difference of these two rapidity variables. And as such, it can either be a rational function, a trigonometric function, or an elliptic function. So the complexity of the system increases as going from XXX to XYZ. And in terms of symmetry, there is actually a quantum algebra underlying all these structures. And this quantum algebra in this case is based on a deformation of the SU2 or SL2 affine Katz-Moody algebra. And we'll encounter some of that a bit later. So many of the structures can be expressed through quantum algebra. And yeah, so just to name the few main quantities or main structures in the quantum algebra, there's the product, which tells you how transformations compose. There's the co-product, which tells you basically how some generator acts on a tensor product of states. Tensor products here are basically multi-particle states or multi-states composed from several spins. And finally, the R matrix is something that is there in integrable systems, and that governs the permutation of two tensor factors. And in that sense, it really makes sense. If you have two particles, they scatter, they pass through each other. This somehow governs the permutations. However, Quantum algebra altogether is not an easy topic, and you have to deal with intricate combinatorics, and you have to deal with nonlinear relations and functions. However, quantum algebras, at least in a more formal sense, with r-matrices, they generalize to higher rank Lie algebras and Lie superalgebras in a somewhat straightforward fashion. So instead of having systems which rely on an SU2 symmetry, you can generalize that to higher ranks and to superalgebras. And constructions for these simple Lie, or especially for simple Lie superalgebras, are known, and their features are quite similar to the ones that I tried to sketch for SU2 and SL2. So we can now return to the r-matrix that I started off with. As I said, this is something that acts on either rows or columns, so it acts on two bosons and two fermionic particle flavors, and it turns out to have quite unusual features. First of all, it has two manifest SU2 symmetries for the 2+2 representations of the bosons and fermions, and these are more or less like rational XXX type. However, it's not just a plain PSU2/2 R-matrix as you would generalize, as explained on last slide here. It's not of this simple kind. First of all, it's not of a difference form. You cannot write this R-matrix as a function of P1 and P2 using just the difference of some rapidity variables. Furthermore, the dependence on P1 and P2 looks like it's elliptic functions rather than rational ones, so it points more in the XYZ direction. And there's also some curious off-diagonal scattering elements. So if you look at bosons and fermions in this slightly bigger block matrix, again you have this block diagonal form, but there are these two off-diagonal elements, and normally they wouldn't exist for usual PSU n/m symmetry, but for PSU2/2 that's a possibility, simply because these are both transforming in different spin 1/2 representations, and if you combine two of the same, you can form a singlet, and so you can take the singlet state from here to the singlet state of fermions. Now this happens to be a very complicated R-matrix then, but it has been observed before in the context of the one-dimensional Hubbard model, which is also a famous integrable model, and for that an R-matrix has been constructed by Shastri, and by doing some transformations this R-matrix is actually of this form. But it has never been so clear what is the quantum algebra origin of this R-matrix. Is there some algebra, some deformation of an algebra that gives rise to this R-matrix in the standard form? That has never been clear. So let me explain this PSU2/2 symmetry algebra a bit, because it has some unconventional features that I would like to point out and that play a role. So let's start with typical PSU2/2. This is something you would know, most conveniently write as a supermatrix, a 4x4 supermatrix, 2x2 blocks. The upper left block and the lower right block are just the SU2 subalgebra, the bosonic subalgebras, and the supercharges sit in these two corners. And when you do the usual anti-commutation relations of Q with Q bar, you find, well, in this case, you find the two SU2s, and you find the energy operator, one component of a momentum vector, if you wish. And that would normally describe the anti-commutation relations of supercharges. But in this algebra, there are additional central charges. So if you have Q with Q and Q bar with Q bar, alike supercharges, they give you some central elements, and these are somewhat exceptional. They can be there because they are in a spin zero combination, and only spin zero can really be a central element. So that's why you have a possibility of them. And in the AdS CFT context, the energy and these two central charges are all functions, curious functions of the particle momentum. The energy has this particular, well, almost relativistic form, and the other two depend also on the momentum in some trigonometric fashion. In addition, you can also introduce a derivation element or a grading element that basically measures the supercharges. So the supercharges Q and Q bar can be given opposite charges under B. So Q would have positive charge, Q bar would have negative charge, and that's sort of the usual derivation that you can introduce for PSU/n/m. But here something curious happens, namely you get some additional contributions from the other supercharge, from Q bar or Q, to these commutation relations. And it's quite clear that all of these additional structures that you find here in connection with these off-diagonal scattering elements, they are all related. They all have the same origin in some sense. But it's not so clear what this origin was. And there, some years ago, we had some useful thoughts which are related to the exceptional superalgebra D21 alpha. D21 alpha is a deformation of OSP4/2, which is another orthosymplectic superalgebra, which actually consists of 3 copies of SU2. Here I always pick one out as SL2, but I don't really care about reality conditions, so SL2 is the same as SU2. So there are 2 copies of SU2 which make up an SO4, and SL2 is also SP2. And the deformation parameter can take continuous values. That's what makes this algebra exceptional. However, there are some special points, and namely the point epsilon equals 0 is special. At this point, these two SU2s together with the 8 supersymmetries form the PSU2/2 algebra. But then there's the SL2 left. And it's not uniquely determined what happens to it in this limit. Either it can yield 3 central charges, as I had on the previous slide, and that's precisely this algebra with the central charges that you obtain. But at the same time, it can also, alternatively remain an SL2 algebra, which acts as derivations on this PSU2/2. That would give you something like this derivation element. But it's either this case or that case, but not both cases at the same time. However, there turns out to be a way to obtain both the central elements and the derivations from D21 epsilon. But if you have to supplement it with another copy of SL2, and then you can go to the limit epsilon going to 0 and perform some contraction. And then you obtain this PSU2/2 together with 3 central charges and also an SL2 algebra, which acts on this PSU2/2. I will call it generators of SL2L. These are called P, and in fact, L together with P describes a 3D Poincaré algebra. So if you work out the commutation relations, L with L gives you L with P gives you P, and P commutes with P. So that's precisely if you put the indices, these are all triplets of generators, then you get precisely a 3D Poincaré algebra from it. The supercharges transform under Lorentz transformations in spin 1/2 representations, obviously, and they commute with the translation generators. And anti-commutation relations of the supercharges give you the momentum generators, but also the SU2s. So that's up to this fact that you get some U2 commutators here, U2 generators here. This is an ordinary 3D Poincaré superalgebra. But what's perhaps the most interesting part here is the contraction and the 3D Poincaré part. So it will be easier to work with a simplified algebra contraction where you start with SO4, which is 2 copies of SL2. Again, I will not really care about the reality condition, and take a contraction limit to Poincaré 3-dimensional, which is SL2 acting on a triplet of momentum generators. That is one step which I will explain, and the other step which is needed for the AdS CFT r-matrix is a reduction to more like a 2-dimensional picture, where SL2 cross C3 reduces to GL1 cross a single momentum or energy generator. We'll see how that works. Okay, now first let me describe the 3D Poincaré algebra as a contraction. You may have seen that. it basically corresponds to the case where you have a 3-sphere or 3 AdS3 space, and you look at a certain point on it and look at the tangent space. Now, at the tangent space, the symmetry reduces. There are only rotations about this, but since the tangent space is flat, you can also have translations within it. So therefore, on the tangent space, you can say there's a 3D Poincaré algebra acting. And so that somehow explains why this, I mean, these SL2s, if you just consider two small translations on the 3-sphere away from the marked point, that will be approximated by translations. And that's how this contraction comes about. So let me explain the contraction in more technical terms. You have generators from both of these SL2s, I'll call them M1 and M2, and you do a linear transformation to a triplet L and P in this way. This is a transformation that depends on a parameter, continuously on a parameter epsilon, and it's invertible, so this would be the inversion, but the transformation happens to be singular at the point epsilon equals 0, obviously, because then P would be 0 if you send epsilon to 0. But you can re-express the algebra relations of the original algebra. Here's just a direct product algebra into the new variables, so generators L and P, and then you get L with L is L, L with P is P, and P with P is epsilon times P, but if you send epsilon to 0, P commutes with P, and that's just the Poincaré or Euclidean structure of the Poincaré and Euclidean algebra. We can also do this at the level of representations for AdS3 and for flat space. And I think that's a useful interlude because representations help us to illustrate some abstract algebra relations that we just had. And we could address the question of how unitary representations of SL2 cross SL2 are related to unitary representations of 3D Poincaré. Well, this at first sight, this does not appear to be so easy. If you look at unitary representations of now the non-compact SL2, these are either of lowest highest rate type or they are principal series representations. But in either case, these are representations, states are labeled by an integer. And since you have two copies of SL2, these would be two integers. So your states would be labeled by two integers. In 3D Poincaré, you know the representations. These are basically on-shell fields, which are characterized by a mass and a spin in 3D, spin under SO2, residual SO2. And so the states are labeled by the spatial components of the momentum vector, right? There's nothing left from the spin degrees of freedom here. So these are continuous variables. These are discrete variables. How can you relate the two? Well, the Casimir, the eigenvalues of the Casimir invariants might be helpful. So if you look at them, that gives you some clues. And we came up with this particular solution here. If you have this discrete set of states for SL2 cross SL2, in this case, we have to use a lowest times highest weight representation. So this would be some one quadrant, basically, where one SL2 acts in this way, the other SL2 acts in this direction. But it's interesting to look at what are the Cartan generators in this direction. It would measure the energy, actually in units of epsilon, where epsilon is this contraction parameter. And in this direction, you get angular momentum, but in integer units. And that helps us to understand how to relate this to a momentum representation. Since this direction is energy, you just basically have to rescale it so that the energy here becomes a continuous variable. And once you go to large enough energies, there will be infinitely many states in each for each energy eigenvalue. And these are characterized by angular momentum. So if you perform a Fourier transform on them, you'll get an angle coordinate. So your states would then be labeled by the energy and by an angle. And those can be translated to on-shell momentum vectors, px and py, by just doing a radial transformation. So phi would be the angle, the direction of your momentum, while p is the magnitude of the momentum, and that obeys this relativistic energy relation. So the result is that if you perform the contraction, which consists basically in sending epsilon to 0, you make this continuous in this way, and you find the on-shell field representation for 3D Poincaré particles. Now, yeah, so we wanted to explore the quantum algebra structures for such an algebra based on this contraction. And instead of doing it for the full quantum algebra, we decided to look at the classical limit to simplify the matter. This classical limit is helping us a lot because it's sort of like the analogy between the simplification that you obtain from going from a Lie group to a Lie algebra. You linearize the problem, and that turns out to be sufficient for the product that leads you to the Lie brackets, as you know. But the co-product turns into a co-bracket, and the co-bracket gives you sort of the deviation from a trivial co-product. A trivial co-product is just an ordinary tensor product transformation rule, but the co-bracket tells you how much you deviate from such a rule in the quantum algebra. So the co-bracket is one element. The other element is that the quantum R-matrix we are interested in reduces to a classical R-matrix, and that is, again, the deviation at first order in H bar from the identity matrix. And these two structures in the classical algebra are directly related, namely you can obtain the co-bracket by a commutator with the R-matrix for any symmetry generator. And there's also the classical counterpart of the Young-Baxter equation. So the classical R-matrix should obey this classical Young-Baxter equation. Let me give you the example of the SL2 bialgebra. So again, we do not really care about reality. SL2 has three generators, a charge generator, a raising and a lowering generator. And let me just, for completeness, state the Lie brackets. Lie brackets, J naught measures the charge of these J plus minus in this way. J plus commutes with J minus onto J naught with some conventional factors that depend on our choice here. We have this quadratic Casimir invariant. This is the total spin operator, if you wish. J squared is J naught squared plus J minus J plus with certain coefficients. And the R matrix can be expressed in a very similar fashion. This is much like an XXZ type R matrix here, where you have a J naught times J naught and J plus times J minus. And that particular choice of R matrix does satisfy the classical Young-Baxter equation. From that, one can compute the co-bracket for all the generators. Co-bracket of J naught is trivial. From J plus minus, it's J naught wedge J plus minus. That's just one particular example, and you can easily explicitly verify these relations here. But what's interesting is now how to perform this contraction that I introduced here to the algebra. And we have now two classical R matrices, one for each factor of SL2, and they both have this form, but if you substitute this transformation that I introduced here, the R matrices take this form, and in particular, they start out with 1 over epsilon squared. So they are divergent, and that means it doesn't really make sense to take the contraction for each of these factors individually. However, you can take a combination of the two, and what you see, first of all, is that these two leading coefficients are actually the same. So if you take the difference of the R matrices for the two SL2s, you remove this, and then you just need another factor of epsilon to kill this prefactor. But you might also add in another term, which is epsilon squared times R1 or R2. Doesn't make a difference because the leading part is the same. And you can add in this additional contribution with some parameter xi. So if you do that, you obtain whatever remains here, well, whatever you get from here, plus that, and that gives you a new classical R matrix, which works for the Poincaré algebra. This does satisfy the classical Young-Baxter equation for arbitrary parameter xi. In fact, it has two independent parameters. So one is an overall factor for the r-matrix, and the other one is psi. And so the number of parameters has not actually changed. The co-brackets for this system would be that the Cartan elements have no co-brackets, have trivial co-brackets. The co-brackets for the rotations are of this form, and the co-brackets for p plus minus are of this kind. And this algebra is actually known as, well, at least the quantization of the algebra is known as kappa-Poincaré symmetry. Here we see the classical limit of it, but in this way we can derive kappa-Poincaré as a contraction of some simple B algebra where the structures take a very regular form. We can now go one step further. That's what we added more recently. Namely, we can reduce this 3+3 dimensional algebra, which is Poincaré, to a 1+1 dimensional algebra containing one rotation and one shift, so one L and one P. The algebra will be, unfortunately, or maybe fortunately, a bit boring because it's abelian. The co-brackets are trivial, and the R-matrix is basically just L cross P, the simplest thing you could imagine. But the R-matrix and the bialgebra structures reduce very nicely. So just by doing the reduction in the way we do it, we know that the R-matrix comes out as something that satisfies the Young-Baxter equation, and also representation theory comes about in a natural way. But it just happens that this algebra here is trivial. This is, however, important because we can extend it by the PSU2/2 that we dropped earlier. If we take along the PSU2/2 for the right, then indeed we obtain a non-trivial Lie algebra, and we obtain an R-matrix, an exciting R-matrix, which has GL1 cross PSU2/2 plus C, the algebra that you actually need and observe for the AdS CFT context. So let me explain how this works. The first step is that you need to apply a certain twist to the R-matrix or to the co-algebra. That is, you take the R-matrix and add a certain diagonal element to it. That is called twisting of a classical R-matrix. So, and this removes some or shifts some terms around. It doesn't change anything about the Young-Baxter equation. And in that sense, it's a valid twist because it does satisfy these particular properties, and that guarantees that the Young-Baxter equation continues to hold. The resulting co-algebra would be of this form. Maybe it's not too relevant why it's that, but that's what you get here. Some of these relations have become trivial now. That's interesting. The second step would be to look at now. I mean, this was just a twist. We look at a one-dimensional subalgebra of the rotations. So the rotations are from a three-dimensional algebra, SL2. We can single out rotations in one certain direction. And here we take this direction to be L0 plus beta minus L plus. Beta minus would be just some parameter that parameterizes our ignorance, if you wish. And the resulting algebra takes this form. So the commutation, there's no commutation relation of L with itself, obviously, because there's only one generator. But there are interesting commutators with the momenta. And if you look at the right-hand side, you notice that only two combinations appear, namely P plus and P minus plus 2 beta minus P naught, these two. In principle, you start with 3. You could have 3, get 3 out. But since you get only 2, this means that there will be a two-dimensional ideal of the momenta. And such an ideal you can always divide out in the Lie algebra, and in order to simplify it. You divide it out by basically setting these generators to 0, and if you set them to 0 on both sides, you'll get consistent commutation relations. So you set P plus to 0, you call P naught P, and P minus would be therefore minus 2 beta P. And the resulting algebra would be L commutes with P, as I mentioned earlier. But by performing a reduction in this way, by focusing on a subalgebra here and dividing out an ideal for the momenta, the R matrix reduces nicely to these two terms. And if you start with the full expression, you see that there are some additional terms, but these terms here survive, and these terms contain generators. I mean, here these belong to the subalgebra, but this generator here does not belong to the subalgebra. However, the other factor in the tensor product belongs to the ideal, and you set the ideal to 0, so all the unwanted terms drop out, and you only find those terms that belong to the subalgebra or that remain after dividing out the ideal. This construction is nice because, as I said, the classical Young-Vector equation follows straightforwardly, and the R matrix reduces on the ideal subspace of modules, so you can apply it to representations right away. Okay, now this was one step of the reduction, and let me finally explain how this really generalizes to the algebra in the AdS CFT context, which is also a loop algebra or almost an affine Kac-Moody algebra. In this algebra, you have, in addition, these spectral parameters, which somehow govern the loop level, and the R matrix takes a different form. You start with this one. This R matrix is something you get after performing a contraction, and here what sits on top here is basically just a quadratic Casimir invariant, and you divide it by the difference of the spectral parameters, and you apply a certain twist. Now, here again, you can define a subalgebra by picking out a generator L, which is again a combination of the three L's. But now you stick in something that depends on this spectral parameter, so that somehow shifts you in the loop level, in the level of your Kac-Moody generators. But well, I mean, for simplicity, you may just view this as a complex parameter for the time being. However, when you introduce this subalgebra, the momenta will generate you an ideal, the algebra will have an ideal, and you can quotient that out by saying P naught is P, P plus is again P, and P minus is P with these prefactors of the spectral parameter put in. If you do that, the R matrix that you have here, you can see how it reduces, and you obtain just terms of the type L times P, P times L, and maybe something for this additional parameter that you have here. But importantly, you get some prefactors which depend on these spectral parameters. And if you look at these combinations, you immediately see this is of difference form, but this is not. So by performing this reduction, first of all, the twist, this twist term is important to eliminate some unwanted terms. But once you start with this twisted R matrix, you do the subalgebra and quotient, you find an R matrix that does not depend on the difference anymore, but also on this quotient here. And in particular, you find some extra dependence on the loop level, some new structures, which is exciting. It's not of difference form. You can also perform this for, I mean, this was for the XXX rational case. We can also do this for the XXZ trigonometric case. And here I only showed you the structure for the Poincaré, bosonic Poincaré algebra, but you can supersymmetrize that, and you can also quantize that in the end, hopefully. That would be the next step. So the results that we obtained in our paper, where we extended this also to supersymmetry, showed how this works explicitly, and also applied it to representations, which in the case of the Poincaré algebra are fields on momentum space. Further steps would be, well, I mean, this reduction that I explained is interesting, but we don't quite know how to interpret it. Somehow a reduction from 3 to 2-dimensional system, but also not quite. This would be interesting to understand also in terms of what does this abstract algebraic construction mean in terms of the physics. Where is the 3D picture sitting? Where is the 2D picture sitting? We would like to, or we are extending this to affine algebras in the rational and trigonometric case. This gives us some interesting structures for the affine extensions. And we then hope to lift this to the quantum affine algebra. And by doing that, we should recover the worldsheet S matrix and the corresponding quantum algebra for AdS CFT as, in the summary, as a contraction and reduction of the quantum affine algebra, D21 epsilon.
Okay, thank you, Niklas. I think Hamid has 3 questions in the chat. Can you read that?
Yes, thanks. Yes, I saw the questions. Yeah, I can only watch this on a mobile phone, so my screen is a bit small. But these are interesting questions. So, first of all, yeah, the first question is, what is the motivation to contract? Is it flat space holography?
Nicholas, can you hear me? I have. I think Nicholas is connected from the chat. Sorry, Nick, can you hear me? If you...
Sorry, I seem to have dropped out. But now I'm
so
back.
We lost you from... Yeah. Would you please answer again from question 1?
Okay, I can answer from question 1. So the question is, why do I do this contraction? This was one point I somehow missed to say in the talk. This was because the quantum algebra constructions are quite well understood for simple algebras, but here we have central charges, we have derivations, and therefore the algebra is not simple. And it's not so clear what structures you would get there. And the contraction is, in this case, is a way to obtain this non-simple algebra, and we can then use the algebras from a simple, the structures from a simple algebra, do the contraction on them, and see what we get, and that's exactly what we wanted to get. So it sort of extends the toolkit of quantum algebra in that case. The second one is why is the Bialgebra important for AdS CFT? One could say that, well, this quantum algebra summarizes, symmetries of the system, but also creation and annihilation operators. So it gives you a way to, do many of the physics things like create particles, annihilate particles, by means of algebra, and you would then hope that this algebra structure is really exact, even non-perturbatively, and you can work with that and really obtain some non-perturbative results, as we have seen, for example, for the spectrum of planar AdS CFT or planar AdS 5x5 strings. And there was a third question. I can still briefly comment on that. What if we don't contract but somehow obtain Maxwell algebra and you would obtain a different structure? That sounds like an interesting idea, interesting thought. The steps we've done there were sort of just first steps, and we really wanted to get the algebras that we needed for this AdS CFT scattering problem, which we can obtain by contraction. But if you can do something else, that might give you something cute and interesting new. Yeah, this is good thought. Is there anything else I could? Anything else I could answer? I've seen those 3 questions.
No, there's no in the chat. Okay, thank you, Nick, for your talk.
Thanks for your invitation.